Good afternoon, everyone. This is Shauna, and this evening I'm going to be going over one of the problems from a supplemental section. It's not in your textbook. Professor Nickdell did provide the problems for you. It's the section on the sample means of sample proportions, the central limit theorem for sample proportions. So let me show you that now. That's this set of slides. Let me put it on the screen. This is our set of slides for this. This is not in your book, as I said. The homework assignment is on Canvas. I'm not going to go over the entire set of slides. A couple of things that you probably need to know before we start that I'm going to put on the whiteboard for you right now. Most of our parameters, remember, those are things that describe populations. Most of our parameters in our statistics have different symbols, and proportions are no different. So if you see a population proportion, that's going to be P, like this, usually an uppercase letter, but definitely no symbol around it. This is the population proportion. Okay. And then we have something called P hat. P hat is a P with a symbol on top of it, like this little circumflex on top of it. That's called P hat, and that is the sample proportion. Okay. Now, in this particular section, these distinctions are going to be really important. The sample proportion, there's a couple of ways that they can give it to us. So let me take you to the slides and show you this. Sometimes what they do is they give you a certain number out of the group. Like they'll say 10 people out of 30, so-and-so, right? So in that case, X is the number of sample units. It could be people, it could be trees, it could be whatever you're talking about. P hat is X over N, okay? And Q hat, the one that doesn't have our characteristic of interest, is 1 minus P hat, just like before. So this is a binomial situation in that sense, that you either fit the condition or you don't. But when we talk about the problems in this section, we're going to be talking about situations where we're using the normal distribution. And remember that the normal distribution, when you hear that word normal, I want you to think about bell-shaped curves. Okay, now if you remember from chapter 3 and also from 6.1 that you hopefully have completed, okay, that we have this continuous curve with the mean, the median, and the mode all in the middle here. What we're doing here is this is not a single proportion. This is a sample of all possible proportions. So essentially, this distribution is the distribution. This is the distribution of sample proportions. Okay. This is the distribution of sample proportions. It follows a normal distribution. That means that for our purposes here, we won't have a mean, a mu. We'll have a mean, but it won't be a mu. It'll be right here, because the mean is always in the middle, the distribution. it's going to be p hat. Okay, our distribution is p hat. This is our sample proportion. It's going to be around our sample proportion here. And then we have a standard deviation, but we're not going to call it that. We're going to call it the standard error, okay? And we're going to have a formula for that. So let me show you this. This is going to the next set of slides here. I'm going to skip ahead some. We're going to come back to the assumptions in a minute. The mean of the distribution approaches the population proportion P, all right? We start with P hat. Mu of P hat is going to approach P if your sample size is large enough. So it's going to approach the population proportion. The standard deviation or the standard error is going to be the square root of P, Q, N. These are population numbers. These are population proportions. N is your sample size, okay? So here's your standard error there. Now, what we're going to do, we have something in this section that we've also had in other sections, but it's more important for us here. And that is we have 3 assumptions that we have to meet. And so, yes, you do have to test these assumptions when you do these problems. You have to test these assumptions. You have to write them out, okay? You can shorten some of it, but you have to show us all 3. You have to show us that you tested. So the assumptions are on slide 10. The central limit theorem, the assumptions. We must obtain randomly attained samples, okay? That means you're going to look for the words simple random sample, random sample. That's going to be stated to you in the problem, okay? But it needs to be stated. The second assumption is that each sample must be less than 10% of the population. Here we're talking about the size of the sample. So what they're saying is that the size of your sample has to be less than 10% of the population. Another way to think of this is that if you take your sample size, which will be given to you, and you multiply that by 10, because the sample size should be 10%. If you multiply the sample size by 10, and you think about the population of whatever you're talking about, the population should be larger than the product that you get. That's the second assumption. And the third assumption is the most important and the most mathematical. The product of n times p should be greater than or equal to 10, and the product of n times q should be greater than or equal to 10. Again, you must test both of these, and they must both pass in order to fit this assumption. But you have to test these assumptions. If you fail any of these assumptions, then you cannot use this method. There will be questions where she will specifically ask you just to test the assumptions. So make sure you understand that. That's what this is. I'm going to go over the first problem in the homework for you. There are, I believe, 8 problems on this homework. They're multi-step problems. And there's quite a bit of content. So give yourself time to do these, even though there's only 8 of them. Let me share the screen and come back to our problem here. It says this: in a recent survey by a shopping organization, 33% of the 1,000 randomly selected Americans said that they were planning on shopping on Black Friday. Suppose that in reality, only 25% did shop on Black Friday. Okay, so before we sort of dive into this, which can be really tempting to do, let's think about what this is actually saying to us. Okay, so we have this percentage, and this is why I wanted to do this problem, because this gets confusing for students. We have 33 here. We have 25% here, right? Sometimes we only have one percentage in the problem. This has two. We have this 1,000 here. Okay. So what are we talking about? All right. Well, the first situation says, are the conditions necessary to apply the CLT, the central limit theorem, satisfied? Explain. Okay. So before we can decide if they're satisfied, let's look back at the assumptions, okay? But we're going to come back to this 33 and this 25. I'm going to bring up the assumption one more time. First assumption, we must obtain randomly attained samples. The samples must be independent of each other. That means that when you take your sample, okay, every element of the sample, every person, every box, whatever you're sampling, has to have an equal chance of being selected, okay? And they have to be independent of each other. So essentially, this kind of goes back to our idea of with replacement. You're putting everything back. You're selecting from the same group, okay? In practice, we grab everybody in one fell swoop. All right, so here, first assumption is randomly selected or randomly attained. If you go back to the problem, you want to look for that wording, okay? So it says randomly selected. That's good enough, okay? So we met this random. So what I usually say is I'll say something like this. I'll say, so I'm testing my assumptions in part A here, testing my assumptions, and I'll say randomization is the first, or random sample. You can write either one, and I'll say stated in the problem. That, so she knows that it's stated. We know that it's there because it's stated as such. Now, section B, the second assumption, is the size of our population. So we're dealing with the size assumption here. Okay, so if we go back to this, my second assumption is each sample, the size of each sample must be less than 10% of the population. So if we go back to our here, we have 1,000 randomly selected Americans. That is your sample size. You have 1,000 people, all right? Now, you have to give this some thought because this won't be stated directly. Who is or what is your population? What is the larger group? In a recent survey by a shopping organization, 33% of the 1,000 randomly selected Americans. Who is this shopping organization surveying? Okay. They're surveying Americans, more than likely in a particular metropolitan area or areas, okay? We don't know exactly. We don't know exactly what their sample was, but is it likely that their population, their entire group of people that they were pulling from, is larger than 10 times 1,000 people? Because remember, it's 10 times whatever your sample size is. In other words, is it likely that this organization surveyed more than 10,000, that they picked from, not selected, but they picked from more than 10,000 people? They picked 1,000, but is it likely that they had more than 10,000? Yes, it is, because here she's going for all Americans. So are there more than 10,000 Americans who would have been exposed to this opportunity? Very much so. So here we're going to say that we're going to say this. We're going to say that this assumption is met because the population of all Americans is greater than, and I'm going to write the expression so that you'll remember, 10 times 1,000 people, which is 10,000. So I'm taking my sample size, which is 1,000, multiplying it by 10, is greater than 10,000. So that size is met. The third one is our condition for the size of our products, N times P and N times Q, which has to do with our successes and failures. So remember here, this is NP is greater than 10, and NQ is greater than 10. And technically, they can be equal, okay? It usually doesn't happen, but technically, these can be equal to and still work. These are greater than equal to symbol, okay? So there we are. Now, where do we go? This is the first place that causes people some problems. So let me go back to that, because what I get is, how do I know which percentage it is? Okay. It says, in a recent survey, 33% of the 1,000 randomly selected Americans. This 33% comes from your sample. How do I know that? Because it says of the randomly selected. And those randomly selected people are your sample. That's not what we're testing. We're testing the population proportion. So what we want to do here is, it says, suppose that in reality only 25% did shop on Black Friday. 25% of whom? 25% is not the sample. 25% is all Americans. That's what we want. So here we're going to use 25%, and here she does the calculation for you. N times P equals 1,000 times 0.25, that's 250. That is definitely greater than or equal to 10. Go ahead and do the other one, which is the complement of this. So if you have 25% of people who did shop on Black Friday, then 75%, 1 minus 0.25, did not. So in this case, we have 3 assumptions, and all 3 of those conditions are met. Randomization, we got a yes, it's random. 10% size condition, we got 10% of that. And NP and NQ are both greater than or equal to 10. So we can use the central limit theorem. We've satisfied our assumptions. We can use the central limit theorem. On part B, we're actually going to describe and sketch the sampling distribution of sample proportions for this situation. This is very similar to sketching a curve like you did in section 6.1 and 6.2, okay? If you remember how you did that, you're going to draw a number line, okay? You're going to have a mean in the middle. You're going to have a height somewhere there. Doesn't matter. But you're going to have some tick marks. These are not going to be equally spaced. So my distribution is not going to look as nice as it should, but yours should be equally spaced. Okay. So I have my tick marks here like so. Now, for those of you who are having a difficult time drawing the distribution, you want to put your dots somewhere below. You want to make sure that it's below. Again, it doesn't matter how far. You just want to make sure that this dot on this side is the same height as this dot on this side. And then you want to do another dot for this level and another dot over here. And what you're getting here is a curve. This is if you're having trouble getting your curve to match. This is one trick for doing that. So you have your distribution. I'm going to use a broader line here. And I'm going to try my best to hit the marks that I made, which I'm not doing because something like this, bear with me, but it looks something like that. Okay, there's my distribution. Now, if you remember the properties, let's go back to that. So here we have, let's look at the properties, okay? We need to do a calculation here. This properties are going to be on the next slide, slide number 11, that the population proportion is going to equal the mean of all the sample proportions. And the standard error is square root of PQ divided by N. Okay, so this is our error. This is what we need to know. We already know what mu sub p hat is. We know that. That's 0.25. I haven't calculated this yet. So what I'm going to do is I'm going to go back now. We'll look at her homework for a minute. Here's our part B. Okay. You put it in, this is 0.25, 0.75 divided by 1,000. When you're graphing, we round to 2 decimal places for the sake of graphing it. You cannot discriminate anything bigger than hundredths when you're graphing. So we want to discriminate that, okay? You want to use 2 decimal places here. This is all the arithmetic for you. Remember, your mean, your p hat, your mu of p hat is 0.25. So you're going to go 0.25 plus 0.01, that's going to be 0.26, 0.27, 0.28, and then you're going to subtract it. So essentially what we have is we have this. Based on the formula, we have, here is our 0.25, which comes from the problem, is our mean here. And remember, when we did our calculation that you saw on the screen, we got, so we ended up with this. We ended up with mu so p hat is equal to 0.25. Again, that came from the problem. And when we plugged it in, we got sigma of p hat was equal to 0.01. So we're going to put that in just like we normally would. And we're going to graph our distribution. So we have 0.24. Remember, you're subtracting here. This is 0.23. 0.22, right? Here you're going to go up by 0.01, so you have 0.26, 0.27, 0.27, and 0.28. Like so. That's our distribution. Okay, so now show you a picture of hers, which is much nicer than mine. Here it is. Okay, there's my distribution. The next question, what is the probability of selecting a random sample of 1,000 people and getting 33% or more saying that they shop on Black Friday? So what we have to do here is for part C, it would be advantageous for us to, so this is part B. Part C, we're looking at 0.33. Now, you don't have to put everything in here. I'm going to draw another distribution. 0.33 is going to be quite far from where we are. Remember, the middle of this is 0.25, okay? And you're only going up by 1/100th of a unit. So this is 0.25. And we're going all the way out here. Let's say that we're going out to right here. This is 0.33 out here. Right? This is 0.33. So that's where we are. Now, here's my distribution. Something like this. This is not the best. Let me draw it better. I can do a better job than that because I need to make this look normal. I'm going to move these tick marks after I draw my distribution. So here, I'm going to say that I'm going to draw this. And I'm going to say that I'm gonna something like this. This is 0.25, right in the middle of it. .33 is going to be somewhere here. So I'm going to draw let's say that 0.33 somewhere way over here. This is where 0.33 is. Okay. And I want to find the proportion that's more than this. So what I'm looking for is the proportion that is in here. Now we use the same technique that we used before. Okay. And if you, I'll put it on the, whoops, I'll put the calculator on screen momentarily, but what I want to show you is that we use the same procedures. So I'm going to get rid of this line here. Oh, not the whole line. Okay, let me undo it. There we go. Come up here and delete that line. Okay, now I'm going to go back to my share here and show you what we have. So we have the line, we have the distribution, okay? 33, if I were going to do something, would be out here somewhere, okay? So it's way far out in the tail. Now, she's reminding you that we have, this is the normal distribution, so normal CDF. Where's the left bound of my region? Well, in this case, it's 0.33. The right bound is infinity. So I'm looking at this. I'm looking at my left bound being 0.33, my right bound being infinity. So then when I write the statement, I say this. Probability of, remember it's not X this time. This is the distribution of P's. So the probability of, and if you look, she writes it for you right here. The probability of P hat greater than or equal to 0.33. So I'm going to say the probability of P hat sample proportion greater than or equal to 0.33, greater than or equal to 0.33. Okay, this is not 33, this is 0.33. 0.33, okay, is going to be, now this is a normal distribution, so the same functions that we followed before, we're going normal CDF from the left side of my region, 0.33, to the right, which in our case, there is no finite right side, but it's infinity, which we're going to use as E99. My mean, which is not my mean, it's my proportion, which is 0.25. And my standard error, which now I have to show you this. When you calculated, let me go back to part B up here. When you calculated this, okay, when you actually calculate the standard error up here to draw your distribution, take this decimal to 4 places, okay? We're going to use this number in our distribution. We're going to use the rounded number for graphing because it's just impossible to be this discriminatory. But here, use 4 and come back and use this number. So this is 0.0137. That's what we're going to use in our probability. So we have, this is 0.25, and then this is 0.0137. Okay, put this in your calculator like we learned last time. Let me bring it up. Here's the calculator. There it is. Okay, let me clear it. So second distribution, normal CDF. Number 2, your lower is going to be 0.25. Your upper is E99. Remember the E is on top of the comma. So second, E99. Remember here, we're using our proportion. So we have 0.25, and then the sigma that you calculated, 0.0137. Paste it. For some of you that don't have this, you might have a line that looks like this with just the parenthesis. But either way, you'll get this line. Hit enter, and you get your decimal, okay? 0.25, okay, hold on. Let me make sure that I put that in correctly. Second distribution, a second entry rather, 0.25. I believe I put, you know what? It's not 0.25. I made an error there. This 0.25 is correct. This E99 is correct, but we're actually looking for not 0.25, but 0.33, all right? I have to fix that on the whiteboard. I gave it to you, but I put it in wrong. There's my answer. And I'm going from 0.25 E99, and I'm looking for 0.33. So let me do this again because I messed up the calculator entry. So let me do this again. Let me stop sharing it. Come back here because I made an error here. This is 0.25. I entered it wrong. I have it written correctly here, but I entered it wrong on the calculator. So let's try this one more time. Let's try this. This is 0.33. So I'm going to clear this out. second distribution, normal CDF, right here. This is 0.33 because I'm E99, the mean is 0.25 and the standard error is 0.0137. Try it one more time. There it is. There's my number. Okay. My number here is small, super tiny. Some of you have been getting mixed up with this. Remember that your probability cannot be any smaller than any larger than 1. This is 2.6, but it's E9, E negative 9. So here, what this means on your calculator is you have this decimal. It means that you have a point, and then you have 8 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 2, 6, 2, 7, 5, 8, 2, 7, 5, 8, 2, 8, 9, 3. So we'll just make that a 9. This is super, super small. Okay. There's a little mistake in her key here. It doesn't make a difference for your probability per se, but this answer this answer 0.01, we do there's my E99. She has this is 2.627 whatever, E negative 9, there it is. And if I round it, it's super, super small. If I round to 4 places, that's going to be 0, meaning that it's so small as to render it effectively meaningless. Now, the last part of this, the last question asks, what is the probability that at most, remember at most is 190 is the most. 190 is the most. So 190 or below, that at most 190 of these people shop on Black Friday. Here, you need to find the sample proportion first. 190 is the most, so the X value, the number of people who shop, is less than 190. P hat X over N, 190 over 1,000, that comes out to 0.19. I'm doing less than 0.19, so I'm looking at this. So I'm looking at a situation where here's my distribution, and I'm looking at, remember, there's 25 in the middle, right? So I have 25 in the middle of this. And I have 0.19 on the left. So this is 0.19 here. I drew it purposely a little further down so I could write and you could see it. This is 0.19. I'm looking at less. So I'm looking at this tail piece right here. So I'm looking at negative infinity, negative E99, 0.19, 0.25, and the 4 decimal, 0.0137. When you do that, let's do that really quick. So we have, this is going to be, let's do this. We have second distribution, normal CDF right here. This is going to be negative E99. Remember, you want your toggle minus your E, so second E, which is on top of the comma, 99. Your upper is 0.19, because it's your proportion. Your mean is 0.25, your standard error is 0.0137. You get an even smaller number. This is 1.5, 1.56 e to the negative 14. So you've got 13 zeros in front of this one. It's a total of 14 places to the left. So you've got 0.000000156. So this is really small. So you get that answer, and you end up with this answer here. It's super small. Let me just check this, but I don't believe that this answer matches. Let me check that. This is normal CDF. Bring it up. Calculate it again. So we have negative E99, 0.19, 0.25, 0.0137. Yeah, this answer comes out to, it's really small. It's not the same answer she got, but it rounded to 4 places, it's the same. And essentially it would be 0. So I hope that helps you. I hope that helps you with the first problem. And I will see you in my next video. Thank you so much. If you have questions, feel free to drop a comment in the video below.